I'm Matthias.
Okay, well, thank you very much for the invitation. It's a pleasure to be back in Sao Paulo, and thanks very much for the opportunity to present my work. So I want to talk about integrability. In the symmetric orbifold. So what this is about is to analyze and understand the ADS-CFT correspondence for the case of ADS3 cross S3 cross, and I'll be concentrating on T4. I think most of what I'll describe will equally work for K3, but I'll concentrate on the case for T4. So in recent years, we've understood this ADS-CFT duality in great detail. Namely, if you go to the sort of deeply stringy regime, you go to the regime where there is one unit of Neveu-Schwarz flux. So this is sort of a very, very stringy size ADS background. What we have shown is that this theory is exactly dual to the symmetric orbifold of T4. And this is a very explicit analysis, so this can be described in terms of a solvable worldsheet theory. So this is a Wessel-Minowitten model, because it's pure Neveu-Schwarz flux. As a consequence, you can work out the entire spectrum of this theory, just like you would work out the string in flat space using Green-Schwarz-Witten type technology. And you can find that the spectrum of this theory matches exactly with the single particle spectrum of the symmetric orbifold, where the string coupling constant is related to 1 over n. So the planar limit is taking n to infinity, but as I'll explain, this actually works also to all orders in 1 over n. So we showed that the spectrum matches exactly the full spectrum, not just the supersymmetric spectrum. You can calculate the full spectrum, you reproduce the full spectrum from here, and we could also do something similar for the correlation functions. So the correlation functions of the symmetric orbifold are reproduced by explicit calculations on this worldsheet theory that we have under complete control, because this is really a solvable worldsheet theory. Now this is obviously great, very satisfactory. It is in some sense a proof of the ADS-CFT correspondence in one specific corner, and you would hope that it's a paradigm for proving ADS-CFT in other contexts. But there's one glaring thing that is missing, in that integrability never ever features in this analysis. What features in this analysis is that this is the tensionless limit. This is sort of the strong, the highly curved limit, and we used ideas from the tensionless string theory to identify the correct objects to compare with. But once we'd identified them, this was just the first a straightforward CFT analysis, and integrability never entered into it. On the other hand, if this is meant to be a paradigm for other examples, you would like to understand how integrability fits into this. Now obviously, there's been much work on integrability for ADS3, so there is a very good evidence that the ADS string theory is integrable. So there's a long list of references, starting with the work of Babyshenko and Stefanski and Zarembo, and then later Horara, Stepanchuk and Zeitlin, and finally Lloyd, Olsen, Sachs, Fondrini and Stefanski. So there's a very good understanding of what the integrable structure should look like, but that integrable, most of that analysis was done in the sort of sigma model approach towards describing string theory on this background. But the sigma model approach is a very poor approach, because we are in this extreme tensionless regime where sort of the geometry of the space is very obscure. The space is tiny. This looks like a free field theory. This is the same sort of problem that SU2, the 3-sphere at level 1, is equivalent to a single free boson. That's sort of part of what makes this work, and it's very hard to decipher this from a sigma model perspective. So in order to understand how the integrability of ADS3 fits into this concrete ADS-CFT correspondence, the more promising approach is to try to understand the integrability on the symmetric orbifold side. And there have been also attempts of trying to understand how that should work, but somehow I think it's fair to say that this analysis was a little bit inconclusive. I mean, there were early papers by Gava and Ryan, then Gomez, Model and Strominger in 2002, then Justin David and Zahu in 2008, and finally Pacman, Rastelli, Razamat in 2009. And they analyzed it, but the answer was somehow inconclusive. One couldn't, I mean, there was no evidence that it's not integrable, but one couldn't really extract the integrable structure from a sort of the perturbative analysis of this dual field theory. And that's a little bit unsatisfactory because, I mean, this is in some sense, at least the moral analog of free n equals to 4 super Mills. And the original starting point of Minahan and Zarembo was to understand the integrable structure for n equals to 4. And it's a bit unsatisfactory that we don't know what the integrable structure is for the symmetric orbifold of T4. Now, given the fact that we've now, I think part of the problem was also that people weren't exactly sure what the symmetric orbifold corresponds to in this landscape. One knows abstractly that string theory in this background will be dual to a conformal field theory that is obtained from the symmetric orbifold by some exactly marginal deformation. But given now that we know exactly what this theory is, this motivated us to have another go at having a first principles approach towards understanding the symmetric orbifold of T4. So my analysis, what I'm going to describe, will purely take part on that side. That has the advantage that I can save about 20 minutes not having to introduce you anything about the worldsheet theory. And it wouldn't just be 20 minutes, but it would be 20 minutes that would safely send you to sleep, and I would have lost all my audience. So I'll only have the challenge of trying to explain to you the symmetric orbifold, which is also a bit of a challenge because I fear that most of you don't have the symmetric orbifold at your fingertips, but I think that's an easier sell. So I'm going to try to explain to you what you have to do to analyze the symmetric orbifold, and I'll also explain to you in which way we've managed to solve this problem, and probably also what were the obstacles in previous attempts of understanding where this integrability comes from. Now, there's one point I would like to stress, which is that the analysis that we are going to perform is, while it will purely take place here, and this is the one piece I'm going to explain about this dictionary, by virtue of the way the correlation functions, which are the things you will have to calculate in order to do the perturbation analysis here, relate to the worldsheet, makes it clear that our analysis, while technically taking part in the symmetric orbifold, morally is really a worldsheet calculation. And I think, among other things, this opens the possibility of understanding where the integrability really manifests itself from a worldsheet perspective, and that will hopefully be a useful paradigm also for the future. So I should first say that this is work together with Rajesh Kopakuma, with whom I've obviously, so this was done together with Lawrence Eberhard, Rajesh Kopakuma, and so this current work I'm describing is with Rajesh Kopakuma and my excellent PhD student Beat Nayatz. And he really deserves a lot of credit for making these explicit calculations work. And so what we managed to do is we made the first principles calculation of the anomalous of the perturbation of the symmetric orbifold. And I think if you want to sort of know the punchline, so we'll be working at large n. So everything will be taking place at large n. And this is obviously what people believe, that integrability will only be visible in the planar limit. So large n is like the planar limit, and we'll understand in a second why exactly this is the planar limit. But what's also important is that, and this is probably what got obscured in previous attempts, that this really only works, the integrable structure really only becomes visible in the limit in which the charges become large, in which the spin chain becomes asymptotic. And for finite sizes of the spin chain, well, we don't explicitly have a spin chain, but in terms of the corresponding quantum number, integrability seems to get broken. That's probably to do with the massless modes that people are always worried about for ADS3, but we just see it as a way of in which this analysis works, and it'll be important for us to take this limit of W large. My aim is to explain to you how this calculation works, at least in broad strokes. I won't go into all the details, but I hope I can convey to you what sort of the idea of the calculation. Before I get into the details, if you're just interested in sort of the punchline, then you just have to listen 5 more minutes and then you can do something else. I think, why is this important? I think it fills an important gap in understanding the integrability for ADS3 because it establishes how the integrability arises on the field theory side. And I think this is something that was important. As I was mentioning before, it is really secretly a worldsheet calculation. So it will sort of suggest insights in how integrability arises from the worldsheet. And thirdly, the perturbation we are studying is the perturbation that switches on Ramond-Ramond flux. So this is also helping us go towards understanding what worldsheet theories with Ramond-Ramond flux looks like. So we are switching on Ramond-Ramond flux. And we have a very good explicit handle on this analysis, which, because it's secretly a worldsheet calculation, tells you how this will look like from a worldsheet perspective. And I think these are all the ingredients, in particular given that the integrability is really a close cousin to what happens for n equals to 4, that would make you believe that maybe by combining these different puzzle pieces, we should have a serious go at identifying what the string theory dual of 3 super-Young mills is, which I think is the ultimate aim for us, to try to prove ADS-CFT by identifying the corresponding dictionary for ADS5, which would be a solvable worldsheet theory for ADS5 cross S5 being dual to 3 super-Young mills in 4 dimensions. And we feel this is going a certain way towards finding all the ingredients that will make this possible. Okay, so this is what I wanted to say in general. So let me now try to give you a lightning review of the symmetric orbifold so you understand, at least roughly speaking, how this works. And then I'll explain to you the sort of techniques of what this calculation are, at least in broad strokes. So the symmetric orbifold is basically you take n copies of T4, and then you divide them by the symmetric group. So if you think about this, so let's try to be as non-technical as possible. So T4 for us will just be 4 bosons, xi. I runs from, let's let I run from 1 to 2. And then we have the x and the x bars. So we have 2 bosons that we write in terms of xi, and 2 bosons that we write in terms of x bar I. And then we have an additional number a, where a will run from 1 to n. And these are the n copies of the T4. And then you have obviously the same for the fermions, but I'll try to stay away from the fermions as far as possible. And then whenever you have a 2D CFT, what you have to do is you're looking at the so-called untwisted sector. The untwisted sector is basically all the things you can make out of this parent theory that are invariant under the action of the symmetric group. This is just sort of the obviously invariant bit of T4 to the n. But if you think about it, and that's sort of well known in general orbifold terms, there will be new solutions, because there will be new periodic solutions, namely solutions that won't close back in terms of T4 to the n, but they'll only close back up to the action of an element of the orbifold group by which you identify the theory. So these are the twisted sectors, and the twisted sectors are in one-to-one correspondence with the different group elements in the symmetric group, and in fact they're in one-to-one correspondence with the conjugacy classes of the group Sn. And the conjugacy classes of the symmetric group are just cycle shapes. I mean, you take any permutation, you write it as a product of cycles, then under conjugation, the cycle shapes, i.e. the number and the lengths of the cycles stay the same, and you just change the entries in each cycle. So the conjugacy classes are just labeled by partitions of n, And we are interested in finding the analog of the single trace operators, and the analog of the single trace operators are the single conjugacy classes. So the single trace operators, which we should find in perturbative string theory, are the permutations that are of the form have one cycle up to length W, and the rest are all one cycles, which you don't write. So what does the theory look like in this W cycle twisted sector? So if we write down so suppose we have the state associated to the ground state of this twisted sector, and it's sitting here, and then you take one of your bosons around. What will happen is if you take if you start with boson dxi number A, and you take it around, it'll come back to you as boson dxi number sigma of A, where sigma of A is the permutation associated to this twist. That's the whole meaning of the twist. You go round up to, it's periodic up to the action of this group element, and this group element I'll take to be the group element that's just the cycle of the first W. So what does this mean? So what this means is that this field doesn't have a good monodromy anymore, but if you take a suitable linear combination of the first W many fields with appropriate phases, you can make states that have a good monodromy, and then monodromies will simply be all the different roots of double root fields of unity. So what this amounts to is the fact that the Fock space in the W cycled sector will consist of the modes of this boson, say, and now they will be, in general, fractionally moded. They will be moded by units of n over W because they pick up a Wth root of unity as you pick them around. So the most general Fock space state will be some bosons of the firm and some fermions. Now the fermions you have to be a little bit careful. And then you have the right movers, so it'll be something like that. And then you have the right moving fermions. Acting on the ground state. So that will be the Fock space in the W cycle twisted sector. And then this Fock space you have to make invariant under the action of the orbifold group. And the invariance condition is basically the thing you would think, namely that the sum over the Ni over W plus the Mi over W, i.e. the mode number, the fractionally part of the mode numbers of the bosons and the fermions on the left, must be equal to the fractional part of the mode numbers on the right up to an integer. Or rather mod z. So in terms of language you are familiar with, you should think of these as being sort of the Magnon excitations, and this is sort of the momentum condition that tells you that it's a zero momentum condition in the W large limit, or correspondingly it has this integer sort of correction to it. So this will be the entire Fock space of this W cycle twisted sector, and obviously the conformal dimension and zero coupling are just the mode numbers added up in the obvious way, and you can read off the charges, so there is no mystery about what the spectrum looks like. And indeed, this is exactly the spectrum that we matched with the spectrum as calculated from the worldsheet theory. So this is the starting point of what we have. Now, for the following, it will be convenient not to work with the actual ground state in the twisted sector, but to work with what you would think of as being the BMN vacuum, like trace Z to the J, and trace Z to the J will be some BPS state. Now this sector, each W cycle twisted sector has 16 BPS states because there are 4 BPS states on the left and 4 on the right, and we'll pick a specific one. So we pick this to be the BPS state, and for whatever it's worth, it's characterized by the fact that it sits in a short representation of the n equals to 4 superconformal algebra, and we take it to be the top one, but it doesn't really matter. It's the one that has the highest conformal dimension, but that's purely for convenience, and we could have done it some other way. It doesn't really matter because you get the entire spectrum by acting with these Magnon operators on these ground states. Now, what we are interested in is to analyze the perturbation by a certain operator. So the perturbing field will come from the two-cycle twisted sector, but what we'll have to do is we'll have to calculate correlation functions where we integrate the perturbing field over the entire space on which our 2D CFT lives, which in our case is always the sphere, because the boundary of ADS3 is a cylinder, you add in plus and minus infinity, it becomes a sphere. So our symmetric orbifold always lives on the sphere. So this is a 2D CFT living on the sphere. Now, how do you calculate correlation functions in the symmetric orbifold? There's an old idea due to Lunin and Matur that is really the smart way of doing this, and it's very nicely pictorial. So the idea is, so here's our sphere. The coordinates of this sphere will always call x, so this will be the axis. And say we want to calculate some endpoint function of these symmetric orbifold fields. So they sit at positions xi up to xn, and at each point, they sit in some W cycle twisted sector. So there's a Wi associated to each point, which tells you in which twisted sector this state sits. And the idea is to sort of undo the twist by going to some covering surface. So what you're looking for is a map from some Riemann surface up here of whatever it is. So this is x1 up to xn. And it will have pre-images here that I call Z1 up to Zn. And they map down. And the condition that this, the way you want to undo this twist is that you're looking for a covering map that has the property that it maps the Zi to xi plus a term times Z minus Zi to the Wi for Z near Zi. So what this means is near xi, you're sort of undoing the wth twist, and while these fields were not single-valued in terms of the x variable, they become single-valued upstairs. And therefore, upstairs, sort of all the knowledge about the twist field disappears, and at the end of the day, what you're going to have to calculate are free field correlation functions upstairs, because you just have free bosons and fermions. All this twisted knowledge has disappeared, and you're just calculating Wick contractions upstairs. Now, as you may have noticed, I've drawn here a funny genus 2 surface, because in general, while this is always a genus 0, the genus of the covering surface is not necessarily genus 0. It'll be genus 0 or 1 or 2 or whatever it is. But the genus of this covering surface is very important because it captures the 1/n dependence of the correlators. So the key observation, and that is, I think, was probably first made by Pachmann, Rastelli, and Razamat, is that the 1/n dependence is captured by the genus of the covering surface. So this is to say the leading term in 1/n comes from the covering surface being a sphere. The terms that are down in 1/n squared come from the covering surface being the genus the torus, and so on. And if you know about how the n dependence should map to the G string dependence from the string perspective, what this tells you is that the genus of this covering surface should be identified with the genus of the worldsheet, because that's exactly how the G string dependence of the worldsheet will come in. So what this strongly suggests is that you should think of this covering surface that from the point of view of the symmetric orbifold is some construct. It's something you dream up as a clever way of calculating the correlator. This should be identified with the worldsheet of the dual string theory. So this would be the guess. And when I said that we checked these correlation functions, that's exactly what we checked. We checked that the correlation functions as calculated on this side localize to the configurations where you get covering maps, and once you do the integral over the string moduli, you get exactly a sum over covering maps, and you get them with the correct, from the correct genus of the worldsheet, reproducing the 1/n dependence. And as a consequence, this is true not just to leading order in 1/n, it's true to all orders in 1/n, because it reproduces systematically the higher order in 1/n corrections. Now, the point I'm stressing this is that for this perturbation in the symmetric orbifold I'm about to do, I shall always be working on the covering surface. And since I'll be working on the covering surface, this de facto means that I'm doing a worldsheet calculation, because the covering surface is really the worldsheet. But for technical simplicity, I'll just treat it as the covering surface of the symmetric orbifold. But that's what I meant by saying this is secretly a worldsheet calculation, because the calculation I'll be doing will be a covering space calculation. Okay, so that's the calculation we have to do, and now we have to get down to business to understand how you actually do this calculation. How am I doing for time? Okay, that looks good. Okay, so now, okay, let me wrap this out. So now we want to, so the first thing you may want to do would be you would want to calculate the perturbed two-point function. That would be sort of the most primitive way of trying to approach this problem. So you know, in a 2D CFT, the two-point function has a specific dependence. So the first take would be to calculate. So suppose we are interested in, so psi stands for one of these guys. So this guy will be called psi. And then so we have this at x1 and x1 bar. And then we have another guy at x2 and x2 bar, say the conjugate field. And then we would have to integrate the perturbing field. So this will be the perturbing field. And then we would have to do the integration over du1 and du2. And because this is exactly marginal, this should give you a function that will be some constant times x1 minus x2 times x1 bar minus x2 bar. And this would normally go like minus 2h and minus 2h bar. And then you would find the anomalous conformal dimension by doing that calculation. So it would come from the log piece in x1 minus x2 when you calculate that calculation. So that's sort of the first principles way of what you would have to do if you want to calculate the anomalous conformal dimension. This is a two-point function, and you've inserted the integrated perturbing field to deform the theory away from the free theory. Now this calculation is actually very, very hard, and we've spent the last half year reproducing the results I'm about to tell you from that perspective. We've now succeeded, but it's been a very painful exercise, and I think the pain we felt is the reason why previously didn't manage to extract the integrable structure, and it has to do with the fact that the 1 over W corrections are very, very crucial in this calculation. So this is not what we are going to do. This is in principle correct, but hard. This is very hard. It's very hard to extract the integrable structure from this. So what we're going to do instead is to follow the sort of symmetry argument that Niklas Weisert used for n equals to 4. Adjust it to the case at hand. So what we're going to do is we're going to pick some subalgebra. So the dual CFT is an n equals to 4, 4 superconformal algebra. It has 4 supercharges, and we're going to pick 2 left movers and 2 right movers. One can also do it in full generality, but for the purpose of this presentation, it's easier to just pick two such charges, 2 left movers and 2 right movers. So let's pick them. So the tildes always refer to the right movers, the untilde refers to the left movers. And there are 4 supercharges, so I can make, there are G's and G primes. So these are the supercharges I'm going to take. And then I'm going to look at descendants that are made from half of the fermions. So I'll call some fermions psi minus. The minus sign of the fermions keeps track of the R symmetry. So this n equals to 4 superconformal symmetry has obviously Virasoro. But then it also has an SU2 level 1 Kac-Moody symmetry, and the SU2 level 1 with respect to the SU2 R symmetry, both on the left and on the right, these fermions will carry charge, whereas the bosons are uncharged. So this is just to explain this notation. So we'll look at states of the form that are made from these fermions in the W cycle twisted sector, and we'll take one of the bosons, and we have multi-Magnon states, and W is this specific BPS state in the W cycle twisted sector. And the idea is that you analyze the action of Q1 and S1 and Q1 tilde and S1 tilde on these states. And then you use symmetry arguments to read off from that what the anomalous conformal dimension of that state has to be. Now at zero coupling, obviously the Q's and the S's, the left-moving supercharges will move these modes into one another according to the usual commutation relations, whereas the action of the right-moving supercharges will annihilate these states, because the left movers and the right movers don't talk to each other, they just go through, and all of these supercharges are such that they annihilate this BPS ground state. So therefore, on the face of it, at zero coupling, these act trivially and these act non-trivially. So what we want to calculate is the first order correction to the action of these right-moving supercharges on some left-moving Magnon state. So what this amounts to is, so we make an ansatz, and let's write it down in the simplest case. So I should have written Q2 here. Q2 tilde, and suppose we just look at a single Magnon excitation, and then we can generalize it afterwards. Sorry, minus a half plus n over w on w. And what you expect on general grounds from the point of view of bit charges that can generate, you will generate states of the form that live in the neighboring sector. So this will be a bosonic mode in the sector corresponding to w minus 1. And likewise S2 tilde on. So these are at first order the terms that are non-trivial, and we parameterize them by saying that they are so there's a sum over m involved here, and we simply write down the states that could be produced with some coefficients that we are about to calculate. So this is an ansatz. So you make this ansatz that to first order in perturbation theory, when the right-moving supercharges act on a left-moving Magnon, they'll produce you a Magnon, a different Magnon. And because the perturbation theory involves this perturbing field comes from the two-cycle twisted sector, is from the two-cycle twisted sector, the fusion rules of the symmetric orbifold dictate that the answer can't lie in the same twisted sector. It has to be either one up or one down, just from the fusion rules of the two-cycle twisted sector with the W-cycle twisted sector. So the aim of the game is to calculate this coefficient, and let's calculate this coefficient from first principles, and that's what we did. So how do you calculate this? This is something which I think Governor Ryan already attempted, except they somehow didn't manage to do the calculation in full generality, and somehow only got this small n behavior of it, but didn't see the whole structure. The calculation is admittedly, I mean, from the way I'm going to describe it to you, you will think it's an easy calculation, and it should be an easy calculation, but it still took us a few months to really do, because it is the devil is in the detail to get all of these factors to work out. So, for example, this CNM coefficient is really what you think it is. You have to take the bra corresponding to this state. So you take something in the W+1 sector. You take the conjugate of that field, which is psi plus a half minus m over W+1. Then you insert the action of S2 tilde. S2 tilde is, sorry, these are Q2s, is G tilde prime plus minus a half. And then you insert the two-cycle twisted sector. The two-cycle twisted sector is this phi 2 of u and u bar. And then you apply it to the state on which you're acting. It is alpha 2 minus 1 plus n over w acting on the w-cycle twisted sector. And the structure of this answer is that this perturbing field is essentially of the form g prime minus a half times g tilde prime minus a half on the ground state of the two-cycle twisted sector. That's what this exactly marginal operator turns out to be. And now you can basically see how this calculation will work. You see this supercharge gets contracted with that supercharge. That supercharge will turn this boson into this fermion, and then the two-cycle twisted sector will turn W into W+1. That's the reason why this correlator is non-trivial. So you can calculate it, and the way you actually calculate it is that you go to the covering surface. So you go to the covering surface. So here you obviously have to do the integral over d2u. This is the perturbing field that you have to integrate over all positions. But because it's a 3-point function, this integral is de facto trivial. So you can think of this basically sitting at 1 point. And then if you look at what you have something living in the w-cycle twisted sector. You have something living in the 2-cycle twisted sector. That's the integral of a field from the untwisted sector. And that's in the w+1 cycle twisted sector. So therefore, you really only have 3 branch points, w+1, 2, and w. And as a consequence, you can simply write down the covering map explicitly. The covering map in this example is just something like w+1 times z to the w minus w times z to the w+1 for the case where u is equal to 1. So this is the explicit covering map. And now, in principle, it's clear what you have to do, right? You simply lift this up to the covering map. This becomes certain, so upstairs you're going to become this free boson. You're getting these supercurrents, this free fermion. And their mode number is determined by taking suitable contour integrals of suitable powers of the covering map. The covering map is explicitly known, so it's just a matter of the technicalities of working this out. And you can work it out, and there's an explicit formula, and I'm not going to write it down because it's just gamma functions galore, but it's totally explicit. We have checked it, and there is nothing wrong with it. And so here I've calculated this for 1 Mach-non. You can see how you would calculate it for n Mach-nons. For n Mach-nons, you basically get big contractions of more free fields up there. But up there, it's just free fields, so you get big contractions of free fields. So you get something you can just recursively calculate, and you can find explicit formulas for it. So we've calculated this coefficient C and M, which is somehow what people hadn't managed to do before. And this is a mess, but it simplifies dramatically for large W. So this becomes very simple in the large W limit. And in the large W limit, we think of this as defining CPQ, where P is N over W, and Q is M over W plus 1. So we think of this as this momentum of this Mach-nons, and it becomes something very simple. It becomes 1 minus e to the minus 2 pi I p divided by some normalization factor, square root of 1 minus p. And then from the overall integral, you get a delta function in p minus q. So you get something very simple, but only in the large W limit. For finite W, this is a mess, and it only simplifies in the large W limit. So here I've explained to you how to do this calculation for a single Mach-non. You can repeat this for multi-Mach-nons. And then once you've got that, then you can run the usual you can run the usual structure. So what will happen is that under this perturbation, this n equals to 4,4 superconformal algebra picks up a central extension. The right movers and the left movers will not in general commute with one another unless you are on the physical states, i.e. the states that satisfy the momentum conservation condition. And we've showed that at finite W that the anticommutator is exactly 0 provided that the momentum condition is satisfied, and at finite W that comes out on the nose. So at finite W there is no extrapolation, and you just show, this is just a way of showing you that you've done this calculation correctly. You have analyzed this perturbation correctly in a way going off shell such that on shell the structure is not destroyed. But then it also tells you what you have to do at large W, where there is some phase factor that is not easily determined, and it tells you how you have to pick the phase factor. And once you do it, you can basically run the usual integrability machine to make predictions for the anomalous conformal dimensions of all of these Mach-non states on these ground states by just using self-consistency and then sort of bootstrapping yourself up to all orders in the coupling constant. So we've done this for the free bosons and fermions. You can also do it for the fractional G modes, which are to be identified with the so you can do it for the G and the G primes. Sorry, is this? And then correspondingly for the for the, so these are the parts of the SU2 modes and the Virasoro generators. And these are, you can repeat the same analysis. The analysis is essentially the same. These are the ones that describe the ADS3 cross S3 Magnons, whereas the free bosons, fermions, describe the T4 Magnons, and you land on the structure you would expect to land. So you find something that has an S matrix, is integrable, and after suitable translation of conventions, it agrees with the integrable structure that has been postulated before. So this is sort of an honest first principle symmetric orbifold theory calculation. So it's like perturbative field theory, but in the context of the symmetric orbifold. It's not using Feynman graphs, because that's not the right language for the symmetric orbifold. It used this covering surface technique, but with that you reproduce exactly what you expect to reproduce. So this is just a big check mark, everything fits together. I think it's satisfying because it fills this gap of understanding how it works for the field theory side, but it also, I think, is instructive because it tells you de facto how integrability should appear from the worldsheet perspective, where you would want to think in terms of string bits and somehow this being the action on the string bits on the worldsheet. So this is where we are. So what we would like, what we are currently studying is exactly the 1 over W dependence, the 1 over N dependence. You would expect this to break down at 1 over N. Studying at 1 over N will mean that you're not just looking at this covering surface, which is the sphere covering, but there is also a genus 1 covering. So you have to look at but there is an explicit formula for the genus 1 covering, which will give you the 1 over N corrections, so you can calculate them. You will be able to see to which extent integrability is preserved or not. We don't expect it to be preserved, but that would be something to check. And then I think the other hope is that now that we've understood this example, we maybe could try to find the Ramond version of that story. So this is the Neveu-Schwarz tensionless version of ADS3 cross S3. But you would expect that if you look at the theory with minimal Ramond flux, there should be de facto a free CFT. We don't believe it's a symmetric orbifold. It's probably something else, like what Nikolai Gromov and others have done is gives you a description of that theory that doesn't look anything like the symmetric orbifold. And one would hope that one can guess a similar worldsheet theory based on sort of the experience we have gained on how the integrability manifests itself on the worldsheet. And that's what we are currently trying to do, to sort of go to the pure Ramond case, which is probably the next stepping stone towards ADS5 cross S5. So I think my time is up, so I'll thank you for your attention.
Thank you very much. Kalia?
Thanks for the nice lecture. Probably will need like 5-hour version of that to understand all details.
We can read the paper. It's the old-fashioned way of doing this.
Right. Well, yeah. So just to understand minor details. So you said you're following Bizert symmetry argument, but so Bizert normally doesn't really require to know anything except for the symmetry, right?
Right. So in some sense we can do better because we know. We can calculate these coefficients from first principles. So that's. But I mean, we are inspired to look at these states because that's what you would. I mean, this is basically the spin chain length changing operator, right? So the two-cycle twisted sector tells you that the twist sector will shift upwards or downwards. So you would expect, if you can interpret this in terms of a spin chain, this would live in the spin chain of length W. And then the first order perturbation will make the spin chain one shorter and one longer. And so these are the coefficients, but we didn't have to postulate many things that you had to postulate. We could calculate. In particular, this is something that's the consequence of a calculation that's not coming out of postulating some self-consistency. And it's a hard calculation, but that comes out honestly as a function. In particular, for finite W, the central extension really vanishes on the nose, and this is something you can just prove. There is no assumption about anything. It's just an honest way of calculating it.
Alessandro?
So maybe a comment and a question. A comment about the k equal to 0 case, because in that case there are equations that describe the spectrum, and there are always also some results.
So by K equal to 0, you mean pure Neveu-Schwarz flux, but with Ramond-Ramond spectrum?
Just Ramond-Ramond, essentially, just Ramond-Ramond flux, no Neveu-Schwarz. You were alluding to that at the end of your talk, right?
Right. So I think what we are aiming for is to find a microscopic 2D, so what's the 2D CFT that's dual to 1 unit of Ramond-Ramond flux?
Right.
So there should be a simple answer, right? This is the tensionless Ramond-Ramond regime. There should be something with a higher spin symmetry. There must be and the question is, which 2D CFT is it? And I don't think that is understood, at least.
So, yeah, while I don't have a direct, so I mean, there is some work, including by Bogdan and myself and all of us on Sachs, about some description of that could be a candidate. But what I wanted to emphasize is that there are numerical results that once you have a candidate, you can go and check.
Absolutely, I completely agree.
Right.
So the challenge, yeah. So it's not that we are in uncharted territory. This is good because we want to identify this theory, and all of these results. There's also results of yours and Frolov on this. So we would want to compare our candidate with what is known. But what I'm saying is that is a problem that should now be within reach to identify this 2D CFT and then try to replicate this story in the Ramond-Ramond case.
And if I might finish the comment, and at least at the first order correction, it looks like the tension really zero, identically zero, is a very singular limit. A bit like the limit of flat space strings in a sense. The first order correction looks already like an interacting theory, meaning that sum of the energy of states containing two excitation is not, the energy of a state containing two excitation is not the sum of two individual states.
Yes.
That was the comment. The quick question, since I'm taking too much time, is in principle, this calculation for Orbifold correlators is done for Orbifold invariant states.
Right.
Whereas this one isn't.
Absolutely.
It is invariant under most of it, but not under the cyclic group. So
correct.
Everything goes through in terms of the technology that you are using.
So this is a very good question. So the fact, what I was straying, that the central term vanishes at finite W tells you that we picked the correct prescription of extending this analysis off shell. Because that would be exactly the place where this would go wrong. I mean, it is a subtle calculation because you are calculating something that isn't legally well defined. So you're extrapolating it, and you have to check that when you go on shell, it reproduces the correct structure, and it does so at finite W, and that comes out of this analysis as we've done it.
Let's continue during coffee breaks, just so people have time to register, those that didn't register yet. And let's thank Matthias for a beautiful talk. And let me just remind